Okay, so I guess we can start. Alright, so I'll share my screen. So before I okay, so this tutorial basically will cover two things. Firstly, if there are any doubts regarding any lecture covered so far, then you can feel free to ask now. Or if not, then the other thing that we're gonna do is look at this tool called Z3, and we'll look at how to use it and the syntax and so on. Okay, so are there any doubts regarding any of the lectures covered so far? Anyone else? Uh, okay, sure. So I'll take that as a no. All right. So I'm going to. So basically, before I start, is Z3 is basically this thing called an SMT solver. Okay. So what an SMT solver is you've looked at these objects like so propositional formulas, conjunctional propositional formulas, and so on. And so it has also talked about how you can have various uh, queries regarding these propositional formulas and all, right? So SMT solvers are basically tools which can help you ask and solve these queries. So what you pass to an SMT solver is a set of formulas. So you have some set of formulae, and you pass this to an SMT solver, and then the SMT solver is generally going to tell you something like sat or unsat. So as you saw, valid and all of the other queries, they can be modeled in terms of sat or unsat. So usually we only deal with sat or unsat queries. So we ask the SMT solver whether this formula is sat or if it's unsat, right? So if the SMT solver comes back saying unsat, that means that the SMT solver is somehow eliminated in all the possible combinations of values the variables can take in your formulae, and you can be guaranteed, or there will essentially exist some proof that these sets of formulas are actually unsat. On the other hand, if your SMT solver says sat, then that means that your formula will have a satisfying assignment, and in fact the SMT solver is going to output a satisfying assignment. So it's going to output what we call a witness, which is something that tells you that okay, there is a satisfying assignment. So that is what it additionally what it will output, right? So what do we mean by formulae here? So like sir said, these formulae can be propositional, right? So propositional formulas is something that's talked about in the last tutorial, or sorry, the last lecture, and so it can be formulas of that kind. It can also be other things. So if your SMT solver can only handle propositional formulae, it's usually called a SAT solver. So SMT solvers, like proper SMT solvers, additional to propositional formulae, it can also essentially deal with formulae involving things like ints, reals, and so on, right? Right. So, so by the way, just sorry for interrupting, but do you have any questions regarding any of the lectures covered so far, Nabin? I guess not. So okay. Right. So it can also take formulas involving ints, reals, and so on. So the exact like logical structure of these formulas I will cover in the next lecture. We'll probably not be looking at too much of these formulas. Maybe a few examples. What we'll focus today is how to, like, what is the syntax of the things that Z3 takes in, and how to write these proposition formulas in a way that Z3 can actually understand, and then how do you use Z3 to call unsat and sat and so on. So Z3 is basically an example of a SMT solver. It's a very widely used SMT solver, and it has been developed by Microsoft. So basically, Microsoft Research is what maintains Z3, the group at Redmond and so on. So yeah, so let's basically look at Z3 now. So okay, so there is a few interfaces for Z3. The first interface that I'll show you is this one particular web interface. So this web interface basically runs Z3 in your browser, and this is good for like just learning and things like that. Then there is this thing called the SMT2 interface. So SMT2 interface will take a file written in a particular syntax. So it requires your .smt2 files. These files are basically human readable files which have propositional and other formulas written in a particular syntax, and then you run Z3 from the command line. Right? And then the third interface is there is a Python API. So okay, there are APIs in multiple languages. There's Python API, there is C++ API. So you can use APIs to directly interact with Z3. And in fact, the Python API is something that we'll be using in this course. So most of the times we'll basically be using the Python API itself, because then you can, based on the result coming from Z3, make other decisions. And call Z3 again and so on, right? So it gives you the most flexibility. But of course, this will be Z3 specific. Whereas on the other hand, this SMT2 API can actually also work with any other. So it's actually this SMT standard is a standard syntax for all SMT solvers. So the same SMT2 file will work with Z3, it will work with, say, there's another solver called CVC4 and other things as well, right? So it's a standard syntax that is common to all SMT solvers, and if you have an SMT file, then you can just run it with any particular solver and it will run. So the first things that we'll look at today is the syntax of this SMT file. The web interface also uses the same SMT syntax. So yeah, so I'll open the web page and show you some like live code, which hopefully won't go too horribly. But before we do that, let's just briefly talk about what the syntax essentially looks like. The syntax is Lisp-like. So has anyone ever here seen any Lisp like language or syntax before? Yes, no. Right. So if somebody is familiar with Emacs, then yeah, you are in a very nice cult, I guess. Um, in any case, so for the other people, basically in Lisp-based syntax, everything is essentially a function call, and function calls are written like this. So normally in a normal programming language, you would write a function call as something like this, right? Instead in Lisp, you write it like this. So the first thing is usually whatever function it is that you're calling, and then you have the arguments and so on. And of course, these arguments might themselves be nested function calls, right? So you can write something like, yeah, so things like this. So expressions essentially tend to look like this. So everything is a function call, and you write the function first and then space separated arguments grouped together using brackets. So the SMT2 syntax is also Lisp-like in the sense that you'll have some command here, and then over here you'll basically just be adding some expression. So for example, if you wanted to write the formula, say a plus or a and b, then you would write it at like this. So and would be a function that can take in arbitrarily many arguments, and you would say and ab. Then you have two variables a and b, and you can have an and over here, right? So for example, so this is basically a and b. On the other hand, say if you have a or b and c, you would write it as something like or a and b c, right? So does this make sense? So if you're not familiar with Lisp-like syntax, just remember its function and then bunch of arguments, or the whole thing wrapped in a bracket. So is this okay? Alright, sure. So now let's go to this actual web page. So right, so this is called Z3 Playground. I'll link to this okay, I'm not sure if I already have linked to this on Moodle, but I'll definitely link to this after this tutorial is over. But basically, what this lets you do is it lets you edit some SMT2 code in this window, and then you can run Z3 here directly, and you'll get some output in this particular window, right? And of course, there is actually there is some text here which will give you a very good and very thorough tutorial about a lot of things in Z3, and you can take any of the code snippets here and paste it here directly and so on. So yeah, we're not gonna like I'm not gonna follow this tutorial specifically, but definitely if you like, I'd suggest you to check this out. It'll give you it'll basically show you the power of Z3, and it has got covers a lot more features of Z3 than what we'll be using in this particular course. But in any case, you can try and check it out and see what all the features are and so on, right? So anything beyond this point we'll probably not need. Yeah. Yeah. Ah, okay, that's a very thanks for that. So I'll try to make this bigger. Okay. Mm-hmm. Yeah, so see, so see, I don't think there is any particular quality setting in. Okay. Mm-hmm. Okay, so I'll make that HD. All right. So does this improve things? Not, not really. Okay. Hmm. Right. So okay. So if I okay, so this text, is this visible? Oh, I see. I see. Okay. Maybe a little bit bigger. Then now is this somewhat better? See, what's happening is if I make it too big, it's gonna apparently. Okay, I can work around that. But is this okay? Hello. Alright, sure. So I'll make it one font bigger than this, and let's see what happens. Right. Sure. Okay. So right. So basically, the first thing that we want to do is what is all the commands there, right? So they're basically commands will let you do a few things. It'll let you declare some variables. It'll let you then add some assertions to the current state of the solver. So I'll explain what that means, and then it'll let you call the solver to basically run all of the commands that you've added in, right? So now the way that you will the way that you will declare variables is essentially this sort of a syntax. So can you see this text, by the way, the one that I highlighted? Okay, sure. So maybe that is also better, right? So okay, there is echo, which will obviously just it's basically equivalent to print. There is also, just I should probably say this, semicolon is basically your comment character, which is yeah, if you're used to Lisp, I guess it's fine. But otherwise, yeah, semicolon is your comment character, and then anything that you like, any other command will basically look like some command here, and then arg, right? So this is basically what things will look like. So okay, so the first thing that we do is basically we declare all the variables that we want to use, right? So a variable is essentially, there is no concept of a variable similar to what a programming language has over here, right? So in a programming language, when we talk about variables, those are usually things which hold a value until we change the value or assign a different value to it, right? So here in Z3, variables are basically just names for values, right? So think of them more as constants in, say, a mathematical formula, right? So in a mathematical formula, if I write something like, say, x equal to y plus 1, then this, in a mathematical sense, it doesn't really mean that we're assigning x to y plus 1, right? It's just that there is some values which are called x and y, and then we're saying that this particular equation holds between them, right? So always keep this in mind, that this is not like a normal programming language where we are assigning things or something like that. Here we're only specifying constraints on a set of values. So what Z3 or what SMT2 syntax basically calls these, what we would normally call, or the closest thing that we would call as variables in normal programming language, SMT2 syntax calls these constants. So if you want to have some named entity that stores a single value, you would declare it as a constant. So you declare const, so this declares a constant, and then you can have whatever, say v1, and then you need to specify what's called a sort. So sort, if you're familiar with C++ and all of that, the intuitive thing that you can think of it is type. It's technically there is a difference between a type and a sort. They're like definitions for types and sorts, and they are different things, and so we'll get into what a sort specifically is tomorrow. But for us, for now, let's just say that sort is basically the type of the value that your variable is going to hold, right? So for example, you have bool can be a sort, so boolean sort, right? So it can be either 0 or 1, right? Okay, so this is right. So there is some details and difference between what a type technically is and what a sort technically is, right? Specifically, when we talk about programming languages, when we say that a variable is a certain type, what we mean is that, like, there is an underlying type system, right? Where you have types and interactions between types, and you can compose types together, and then you can say that a variable belongs to a certain type, right? So unlike that, we don't have a similar sort system, but at a very fundamental level, sorts behave like types, in the sense that if you say that v1 is a constant of type bool, or sorry, of sort bool, that means that the values of v1 is going to only be 0 and 1, right? So what sort is essentially is that it is going to give you the set of values that is this particular variable can take. So it's going to fix the possible values that this variable can take into some possibly infinite set. So things like integers can take infinitely many possible values. And it's also going to fix what operations are allowed on this, right? So in that sense, it's very close to type, but they're also technically different in the sense that you can't, like, there is no notion of combining sorts together, unlike the notion of combining types together in something like, say, C, where you can have you can build a struct out of some types, and then that is a new type, and so on, right? So yes, this is basically the idea of a sort. It's kind of like a type of a variable, but also technically different. So I don't want to say it's a type of a variable, because then there are differences between types and sorts, but it behaves exactly like the type of a variable. Specifically, what it does is it'll in this particular case, for example, it'll tell you that v1 is something that can either be 0 and 1. And what can you do with v1? What are all the functions that can take v1 as an input? Those are and, or, not, and so on, right? So does this make sense? Okay, sure. So now we have this. So let's have two such, right? And now what we can do is we can add an assertion. So what an assertion is basically a constraint that all the variables declared so far need to satisfy, right? So we can say assert and then some expression involving v1 and v2. Now in a normal programming language, if you're familiar with things like assert statements, what happens is that you'll have some execution going on, and then when you hit the assert statement, if the program is going to be like if the program actually program states or satisfies this particular assert that you've added, if the assert expression evaluates to true, then the program continues. Otherwise, it just crashes and burns with some error messages, right? Here, assert's not like that. Again, assert is going to put some constraint on the variables that you have, right? So, for example, if I say assert, say, and v1, v2, right? So now what I'm saying is that I have a formula that is basically and of v1 and v2. So this is basically the formula v1 and v2, right? And I am telling z3 that assert this formula, that is, make sure that this formula is true. So z3 will have inside it its own set of assertions. So usually it's a stack of assertions, but we can like not worry about that. Like, let's just consider it to be a set of assertions, right? So it's going to have a set of assertions. So it is going to have some assertion assertion 1, assertion 2, and so on, right? So you're going to have some set of assertions like this. And then whenever you ask z3 that, okay, whenever you pass the command check sat to z3, so this is basically the command that you pass, then it's going to take, so if this assertion is 1 is phi 1, this is phi 2, and so on, then it's going to check if this formula given by phi 1 and phi 2 and, you know, up until whatever phi n if you have, it's going to check whether this formula is satisfiable. So it's going to basically try and find combinations of the values for each one of your variables so that all the assertions that you have added hold, right? So that is the idea. So whenever you add an assertion, you're telling Z3 that no matter what happens, if you give me an answer saying that the variables are satisfiable, or if you give me some output for the values of the variables, it should satisfy this assertion. So it's a constraint that you're putting on the variables. If you go back to the 3 chair examples, like the 3 person sitting in a chair, that example that Sir talked about, there was phi 1, phi 2, and phi 3, right? You could think of that, each one of those things as being assertions, right? So this is basically, over here we are adding just one assertion, right? Okay. So now we have some variables, we have some assertions. Now what we do is we do check sat, right? And now we have given Z3 all the commands that we need to give it to run something. And if you press run, it gives us an output saying that it's sat. So what is Z3 telling us now? That it's telling us that, okay, it can actually find values of variables for V1 and V2 so that all assertions hold. And in this case, that's not surprising. Can someone tell me what the values of V1 and V2 might be when, so that like all the assertions here will hold? There is only one assertion, but yeah. Exactly, right? So now we can ask Z3 that, okay, you're telling me sat, but like I said before, an SMT solver is supposed to also output some witness, right? So this, you know, we can call it a witness and we can call it other things, but in the context of SMT, an assignment, a set of assignments for all variables is called a model, right? So model is basically something that is going to take a variable and give you a value, right? And that value is going to again respect the sort of the variable. So it's Z3 is not going to give you an integer value for V1 because again, but when I'm saying that V1 is of sort bool, I'm fixing all of the possible values that V1 can take, and I'm also, you know, fixing the interpretation those values will have, right? But essentially it is going to take a variable and give you a value. And we can ask, so whenever Z3 says sat, it will only say sat because it has definitely found a model, and we can ask Z3 what that model is by doing get model, right? And now if you run it, it is going to print out some model, right? So now notice that it's going doing, okay, so there is a lot of syntax here, but essentially what it's printing out is that the value of V2 is true, and the value of v1 is true. Okay, so that is all that is being printed out over here. So just to unpack this syntax for a little bit, it is essentially defining a function. So there's a difference between declaration and definition, right? So when you declare, you don't have to give a value. So if I say declare a constant, it means that I don't want to give a value to that particular constant. So that's why when I said declare const v1 and v2, I didn't have to specify some values. On the other hand, I could have also said define const v1 of type bool and then specified a value, right? So in that case, I'm just, then v1 or whatever would just have been some placeholder for a particular value or value of an expression, right? So I can do something like this as well. Yeah. Define const v1 of type bool with value true. Okay, v1 will not be allowed here, but v3, for example, right? So then, of course, if I run this, it's going to also tell me that v3 was also value true, right? So here v3 I'm saying is that it's just another name for the value true, right? So if you look at the output, every command here is a defined fun. Fun stands for function here, right? So define const inside Z3 or specifically Z3 definitely. I don't know if it's generally true for SMT2, but definitely inside Z3 actually treats constants as a special case of functions, right? It treats so in general you can actually declare a or define a function with as many arguments and whatever output values, so something like this, right? So here it is declaring a function f that is going to take an integer and a boolean and it's going to output a boolean, right? And then Z3 can actually solve out what this function should be. So in that sense it's much more, it can solve out much more complicated queries and so on. But essentially if we define like a function that has got no arguments but has got a return type, then for all intents and purposes that is basically just a constant, right? So if you have a function that doesn't take any arguments and gives you out a value, then that is the same thing as a constant, right? Okay, then just give me 1 second. Hi. Yeah. Yeah. Okay. Right. So I'll. Right. So I think it will take another half an hour. So. Yeah. Sure. Okay. Right. No, I do. I can get more. Yeah, this is very close to Tuka's flat, if you know. Actually, didn't know that when you made me the offer, but yeah, it's very close to Tuka's flat, so that way you can calculate. Yeah, probably. So I'll probably have to get back to the meeting right now. So maybe I'll just ping you. Yeah, definitely. Sure. Thanks. I'm really sorry. So there was some call from the office and all. Right. So as I was saying, basically Z3 treats constants as the special case of function where it's a function that takes in no argument. So I mean, you can just think of this as some sort of, mental gymnastics. So, but like, if you have a function that doesn't take in an argument and just gives you out a value, that is essentially identical to being just a single value, right? So there is no, you know, there is nothing special or anything going on over here, but essentially it treats um, functions with no arguments as being the same thing as constants, right? So that is what you're seeing over here. It's saying that okay, whatever model that I have, you could have generated the same model by using these particular set of commands, right? So you're going to define a function, call it v2, that doesn't take in an argument. So that means basically we're doing define const v2, and that has got sort bool. So as a function, it takes in no arguments and returns a bool, which means it is basically a const of sort bool, and the value is just going to always be true, right? Okay, so this is basically um, the gist of how to use Z3. So any questions so far? Have I lost people at any point? All right, great. Okay, sure. All right. So, right. So now let's try something a little bit more maybe interesting. I don't know. Yeah. So I'm going to add an assertion here. And again, this is because of the zoom, the rendering of this fonts is a little bit weird, but hopefully it's visible. So I'm going to add an assertion saying this. Right? Now what's going to happen when I run it? Can someone give me a prediction? So you're saying v1 will be false, right? But there is also this assertion. So does v1 being false, or can there be an assignment where v1 is false and this assertion is true? Okay, I'll just keep the, yeah. So can there be an assignment where v1 is false and the first assertion is true? Right, so there cannot be any such assignment, right? So then what's going to happen? What will be the output of, say, the first check sat command? Right, so let's run and see if that's what's happening. Yeah, this says, okay, so it's, okay, firstly, let's comment this out. Yeah, so it says unsat. And of course, we got an error last time, because then if it's unsat and we do a get model, then it's actually going to give us an error saying, okay, it's unsat, you can't do a get model if it's unsat, right? Unfortunately, there is no way to actually, there's no like if then else statement where you can check the output of check sat and based on that decide whether to run get model or not inside SMT2 syntax itself, right? So for that, you'll have to use some sort of an API. Like with Python API, all of these commands will turn into functions where you somehow build an AND expression or build a NOT expression and use, add assertion or something like that, some function there will be. And there will be some similar function called check sat, and that will output some value saying sat or unsat. And then based on that, you can actually decide whether to call get model, right? So which is the reason why usually people use APIs when using Z3. But there is this SMT syntax, and you can there are also wrappers which somehow use command line and the SMT syntax in combination, so that you don't have to use an API, because an API is going to lock you into Z3. You can't say switch to some other SMT solver if you think that will give you better results, right? But in this particular course, we'll stick to Z3 and we'll stick to the Python interface mostly. Okay, so far so good. Now let's build a little bit more complicated example. So I'll try to live code this, but I have two possible things that I can maybe try. So do you want to see the chair example, or do you want to see something like, say, a n queens or say a 4 queens problem? I mean, 8 queens will be a kind of a pain to write, so 4 queens maybe. Yeah, which one would you prefer? Queens. So we have 1 vote for queens, 2 vote for queens, I guess. 4 queens, okay, sure. So 3 vote for queens, and there are 7 people. 1 more person. All right, cool. Right. So we'll have some queens, right? Okay, sure. So let me ask you then, how will you model queens, right? So what will your variables be firstly? So like for example, if you remember the chair problem, there we sort of each variable, so we had one variable for each chair and person combination, right? So a variable there was basically, does this person sit in that chair, right? So in that sense we had three chairs and three people and hence nine variables over there. So here what is going to be a variable? Any suggestions? Right, we can do that, right? So we can say that we'll have, okay, so with four queens, that is 16 variables, which is, as you can imagine, kind of, it'll be a long thing to write, but yeah, definitely, we can do occupied and not occupied for each square, right? That is probably one of the, like, easiest way to do these things, right? So that will mean that we'll have to write out uh, 16 solutions. So with your permission, I'll just reduce it to 3 queens if that's okay, although that is kind of trivial. So that at least I have 9 solutions, which is a little bit like 9 variables, which is, yeah. Yeah, sure. Okay. Alright. So let's do that then. So let's say that O for occupied, and then, you know, we'll have the rows numbered 1 2 3 and columns numbered 1 2 3, right? And then I have this and copy it over 9 times. Right, so 1 2 3 4 5 6 7 8 9, I've got 10. Alright, sure, let's label and hopefully we'll be able to. You'll probably have an Emacs macro for this, right? I'm just like joking, by the way, don't like. Right. Um, right, so these are all the variables we'll have, right? Okay. So now what will be the constraints? First assertion. Okay, so what, or, you know, before we write the assertion, let's write a comment. What does this assertion do? Right, so we'll have to check the row, check the column, and check the two diagonals, right? So there are only two diagonals. No, there are actually more than two diagonals, but yeah, we'll have to check the row and the column, right? Sure. So okay, so first assertion, what will it do? Will it check the rows and the columns? How are you going to divide this up? I mean, see, all of these is, you can, you know, do whatever you prefer. So which is why I'm asking you, how would you want to divide it up? Do you want a single assertion for both rows and columns? Do you want one assertion per row? So we'll have 3 assertion for 3 rows, 3 assertion for 3 columns. How do you want to do it? Yeah, yeah. So Nabeen is asking, can't we use something like a 2D array? Definitely, we can use. So that's a very interesting question. So in fact, we can use. So the SMT solvers have support for arrays, right? So there is something called array theory, and you can use arrays to um, encode problems. And in fact, one of the biggest things about using arrays is that you can actually leave n to be a variable. So if you have, say, some, you know, more complicated version of n queens where your query is asking something about n itself, right? Then the only way you could encode that is using an array. So definitely you can use a 2D array. There are, so okay, to be fair, I know that there are 1D arrays. 2D arrays, you can probably do it, but it will be a little bit more complicated. You will probably have to do some flattening. But other than that, definitely you can do it using an array. However, it is a lot more complicated and a lot more temperamental, in the sense that you'll have to understand things about array theory to use it in a way that it will, you know, not hang and stop you from giving an answer, like stop giving an answer to you. So that you'll have to make sure, because once you bring in arrays, things become undecidable in general. Things are already exponential, so it's bad enough, but then it'll become undecidable. So that is something that you have to take care of, and I don't want to basically use array theory right now. I think that will be getting ahead of ourselves. So yeah, definitely you can use 2D arrays, but then you can imagine that um, the sort of the variable that is an array, that's a very complicated thing, right? So it's much harder for the solver to handle that. There is another way to encode it, which I'm actually going to show, but that is not going to necessarily use arrays. That's going to be something even a little bit simpler than that. So okay, so like I was asking, first assertion, what will it be? I'm just going to use the first assertion to be, let's say, check the first row, right? If that's okay. So let's say that it's going to check whether there are two things in the first row, right? So that means that it should not be either of these things. So it should not be, say, so between O11, O12 and O13, there should not be a situation where two of them are true, right? So how can that be? So that can be if O11 and O12 are true, or it can be if O11 and O13 is true. Sorry, so this will be this way, I think. And O11, O23 being true, right? So we have these, and then we are going to say that it's not true that like either of them is true, right? So if either of these three things, O11, O12, O11, O13, or O11, O23, sorry, O12, O13, not O11, O23, but if either of these things are actually going to be true, then that would mean that you have a situation where there is two pawns on the same row, or two queens on the same row, right? Does that make sense? Yes, I'm saying that. So suppose this assertion is going to check whether there are two queens on the first row, let's say, right? So that can happen. So basically, I'm boiling it down to saying that okay, there cannot be two of the variables between O11, O12, and O13 cannot be true, right? So that is basically, I'm saying it in this way, that it there are three situations. O11 and O12 are true, O11 and O13 are true, and O12 and O13 are true. So there are three possible ways in which two of these two variables can be true, right? And I'm saying that okay, neither of these situations should happen, right? If so not of, odd of, and of all of this, right? You're right. So does that make sense? So this is basically the formula that we'll have. Okay, so far so good. Just before before we write more stuff, let's do a check sat, just to be sure that we don't have any syntax errors. Missed a bracket or something like that. So let's run this. Of course, there's a syntax error, no? Probably mixed a bracket. So this one goes with this goes with this. These are all okay. This and this. Alright, there will be extra bracket over here. Right. And it's giving us something, right? So notice that it's giving us all of these things being false. So we have to make sure that like we have at least one rook, at least one queen in each row, and so on, right? So okay, so I don't see that I have too much time, so I'll basically leave this as an exercise to you, but like, can you imagine how you would keep adding such assertions? So you'll need to add two more for the rows, and then three more for the columns, and then similarly for each diagonal, right? So, like, can you see that you can do this, and then you can run Z3, and it'll give you some output. You'll also need to add constraints like, there should be at least three queens. So at least three of every one of these variables should be true, right? So is this more or less okay with people? If I right, so you can see doing this. So for example, if there is an assignment where you're asked to do this, you'll be able to do this, right? Yeah. Yeah. So for three queens, it'll be unset. Yes. There is no way to write like arrange. No, I think. Is it? Yeah, there is no way, right? Yeah. And you can actually try that. You can actually try and see, like, that'll be a computative proof that there is no solution to three queens, right? Yeah. Okay. So so yeah, this is basically one way of doing it. Now I'll show you a little bit smarter way of doing it, which I will actually be able to like code up completely. But there we're actually going to, okay, so I said that I won't go too much beyond bools, but we are actually going to try and use something that is not a boolean. So what we're going to do is we're going to have three integer variables. So we know that has to be a queen on each row, right? And we also know that this particular queen can sit between column, it can either sit on column 1, column 2, or column 3, right? So since we know that there will be one queen per row sort of a situation, we can actually have, for each row, we can have an integer variable that is going to say whether or not, or that is going to say which column the queen of that particular row is going to sit in, right? So does this make sense? So for example, we're going to have an integer variable for row 1, and this is going to be a sort int, and if this one is 1, that means that there is a queen in row 1 column 1. If this is 2, that means there has to be a queen in row 1, the queen in row 1 is sitting in column 2. Similarly, if it's 3, that means the queen in row 1 is sitting in column 3, right? Okay, sure. So it's clear to everyone. So notice that just by using an integer variable, we've already implicitly encoded a few things. We implicitly encoded that there has to be exactly 3 queens. We implicitly encoded the row constraint, that there has to be exactly 1 queen per row, right? So those two things we've already implicitly encoded. So then, all we need to do after all of this is to encode that the column constraints and the diagonal constraints, right? So let's do the column constraints. So the column constraints in this case will then be that, so what is the situation that is equivalent to 2 queens being on the same column, right? It's the situation where the values on those two columns are the same, right? So if, say, for example, R1 and R2 are the same, that means the queen in row 1 is sitting in some column and the queen in row 2 is sitting in the same column, right? So then we have a column conflict there, right? So then your constraint is going to be that R1 and R2 should not be the same, right? So then the queen in row 1 and row 2, they don't like share the same column, right? So let's say that we have, let's add, that as a constraint, right? So not R1, and you can say equal to. So you can say something like this, equal to R1, R2, right? And again, equal to is also a function. So you have to say it like this. It's like an infix sort of a syntax that this follows, right? And similarly, you'll have, so again, let's copy this. Right? So we'll have the similar thing for R1 and R3. Yeah, sure. Yeah. Right. 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 Okay. Okay. Thanks. Thanks for picking up. Right. Sure. Sure. So let me. Maybe I should have drawn a picture. So imagine this is the. Yeah. So imagine this is the s- like chessboard that you have. Right. So then, what we know is we know that in each row there has to be exactly one queen. Right. So it is a well-defined. Yeah, right, right, right. So we know that there has to be exactly one queen per in each row. So we can say that like R1 is going to be which column in that particular row is occupied by a queen. Right, exactly. So for example, if you have this sort of a situation, then you have R1 is equal to 2, then it's this one is 1 and this one is 3, right? Right, sure. So so then these constraints now also make sense, right? Because the only way you are going to have a column constraint, so if you have a column constraint here, that means that the numbers for, say, this is R2, 3, 4, 5. Yeah, so it's, and that is an equivalence. If they are same, there will be a column conflict, and if there is a column conflict, they will be same. So those two concepts are equivalent, right? So that means that basically, yeah, go on. Yeah, so the row constraints are handled implicitly for us. So that in some sense comes from free with this encoding. Right. So then we have so these are basically our column constraints, right? So let's just run it at this point and see what we get. Right. So we're getting one, and then the rest is zero. But it's not supposed to be zero, right? Like we are using one indexing here, so zero doesn't mean the first column. Zero is actually some out of bounds number that we're getting. Of course, that is fine because we have never specified that R1, R2, and R3 should be between 1 and 3, right? Yeah. So we've forgotten to do that. So let's do that. and and then so we have 1 is less than equal to R1, and um, okay, so maybe we'll do it this way. Yeah, so 1 is less than equal to R1. Right, so we have this one for R2, and again this is just rendering weirdly because of the zoom level, so sorry about that. And R3, right? So we have this, and then let's similarly we'll have, you know, a greater than equal to situation, the dual of it in some sense. So we'll have um, greater than equal to greater than equal to, right? So 3 should be greater than or equal to R1, R2, and R3, right? And now let's run. Uh, right. This page has frozen up. Okay, so let's give it a time, some 1 second, something. In general, running it inside a browser is not the most efficient way to do this, and SMT is fairly uh, resource heavy. Alright, fine, I'll stop it, I guess. Okay, so let's try again. Alright, fine. Let me just, maybe this will be faster to type. Sorry about this. Okay. Okay, so let's write this as 3q.smt2. Okay, so I'm going to run Z3 from the terminal itself, because that is the browser page sort of crashed. So the way you do that is just write Z3. So once you have it installed, you'll probably have something called Z3 in your path, and then if you just do Z3 this, it should run, right? Of course, now it didn't give any output because I didn't have checksat or get model. Right, so now let's run this. Yeah, and now it's giving me 132. So what is that? That is basically, sorry, so this is here, let me bring it here. Right, so that is basically, if we have our board like this, this is 1, this is 3, this is 2, right? Now of course this is still, it's not a solution to like 3 queens because we have not encoded the diagonal constraint. So by the way, I sorry for switching over to the terminal, but it's still clear what's going on, right? Yeah. Yeah, it gives you any one possibility. In general, you don't have any control over which possibility it will give you. So Z3 does allow for things like you can define some objective function and ask for some optimal model as well, right? But that again, that will take a lot longer, and oftentimes Z3 is again going to hang up on that, because when you ask for the optimal, Z3 will like only give you something if it can guarantee that that is indeed the optimal, right? So again, that is going to make things a lot more complicated for Z3, which means there will be a lot more crashes and not crashes but freezes for you, right? So in general, Z3, like, be prepared that Z3 will just freeze anytime, because these are exponential and very easily things become like intractable here, and the boundaries, like, there's like a a cliff that you can, above it you're fine, and then suddenly you fall off the cliff and things are just freezing, right? It's not even a smooth transition. Yeah, so that is something that is just the nature of the SMT problem essentially, or maybe the nature of how we've been able to solve the SMT problem so far. Yeah, okay, you're saying? uh, Okay, sorry, sure. So any other questions so far? So let's just write the other diagonal assertions. So how will we write the diagonal assertions? Somebody say that. Maybe something. How will we encode the diagonal assertion? So let me go to the picture. Hmm. Right. So let's generalize that, right? In general, if you have rows that are between, say, rows that are j apart, and their values are also j apart, then that means that they are on the diagonal, right? Yeah, with the three you also have like diagonals that can happen two apart, right? Yeah, one and three is going to also be there. So let's just write those things, and again this is going to be still quite a bit, but so not equals, so um, r1 and r3, if you subtract it, it should not be equal to 2, right? So similarly r3 r1, right? So okay, actually, so r1 and r3 should not be more than 2, r1 and r2 should not be more than 1, and r1 r2 r1 r3, and then r2 and r3 should not be more than 1, right? This is okay, and now we have to just flip the r1s and r3s over here, right? So we do this, and right. Right. So does this make sense? Is this all of the diagonal constraints covered? Somebody say something. So okay. So what I'm saying is, maybe this is not making too much sense, right? So what I'm saying is that like so these two statements, if you look at it, this one and this one, right? What this is saying is the r1 minus r3 should not be 2, because if r1 minus r3 is 2, then what does that mean? That means that like you have essentially some situation like this, right? So something is, so r1 sorry, so you have r1 minus r3 is 2, so you have something here and something here, for example, right? Or if we imagine like say a huge chessboard, a much bigger chessboard, just for generality, then r1 minus r3 being 2 means that you have maybe two queens which are 2 apart this way and also 2 apart this way, right? So they have to be on the same diagonal. And then similarly r1 minus r2, it should not ever be 1, right? Because if you consider r1 minus r2, those are consecutive rows, right? So we have r1, so let's say that this one is r1 and this one is r2, then r1 minus r2 basically is the distance between the two things sitting here, right? This distance. And if this distance turns out to be 1, then that means that you have those two things are in the same diagonal, right? Similarly, r2 minus r3 should also not be 1. But then you can also flip things around and say r3 minus r1 should also not be 2, right? Because again, if you were previously looking at this and this, so now we are saying this and this can also not hold, right? So r3 minus r1, it should also not be 2. So what we want to say essentially is ri minus rj, mod value of that should not be equal to I minus j, right? And now I have basically enumerated this formula for all combinations of I and j. That makes sense. So I've expanded this to ri minus rj not equal to I minus j, and rj minus ri not equal to I minus j, and then I've expand, like, instantiated this formula for all combinations of I and j. I've just wrote out all possible such formulas that you'll get for all combinations of I and j. So does that like sort of make sense here? So everyone? Okay, sorry. By the way, it would really take 1 hour to get a working DNA on our machine. Right, right. So I don't think that it would. I just wanted to give a very generous upper bound there. Okay. So it'll probably take much less than 1 hour. 90% accuracy you should probably get within 10-20 minutes. But then I don't have any way of guessing, what machine that you would have. So on my end, it takes like 10-15 minutes per thing. But I have somewhat of a beefy machine, so I didn't want to like, yeah. See, you can even spend less than 1 hour. The only, like, but if you don't get like some accuracy, then just the graphs won't really look like what I'm expecting them to look like, and hence you not get the intuition that I'm hoping that you might get from this end. That's all. That's the only reason I said 1 hour. So this was the question regarding the assignment that came out, I think, yesterday late at night, by the way. Yeah, so sorry for that interruption, but like, is there any question regarding this? People say yes or no. Hello. It's okay. Cool. With everyone. Okay. All right. Sure. Sure. All right. Sure. Okay. So let's just run Z3. Yeah, it says unsat, right? And that is what we expect. So this is basically what I wanted to cover with this thing. Now, are there any questions in general? If not, I want to know what operating system you guys are working on so that I can tell you how to install Z3, because you'll need to install Z3 to really make use of it. You can directly start playing with it using the web interface, this interface, but like you saw, this interface is not particularly good for doing actual work with Z3. But on the long run, you would want to install it. So what OS? So firstly, is there any question? Okay, sure. So if there are no questions, then what OS are people working on? Right. So people who are on Linux or on Mac, it's going to be very easy for you. So both on Linux and Mac, what you need to do is for Linux, whatever Linux you have, if you have Ubuntu, you can just install, I think it's called Z3-solver on the official, on the official packages. So you can just install Z3-solver via apt, if I remember correctly. And so you need to install two things. That is Z3, and then you can install the Z3 API via Python. So via pip for Python, right? So Z3 API for Python is also available from your standard repositories as well. Yes. So people who are on Windows, I'll have to actually see. So Z3 you can actually install. So how many people are on Windows right here? So 2 people we have, and I think we saw 4 responses before that. So yeah. All right. So okay. So people who are on Ubuntu, or Linux, it's not going to be an issue at all. Or even on Mac, with Mac you have Brew. You can install Z3 and the Python API, both of them for Brew. With Windows, you can install Python API via pip. That will work. Z3, I think you'll have to probably compile it. I'm not sure. I was right, so I'll have to basically check that. But basically, with Z3, you'll probably have to get a particular build for Windows. So let me just, yeah. So by the way, they say theorem prover, but like it is really an SMT solver. So let's see what kind of releases they have, if they have. Yeah. So right. Hmm. Okay, I think the easiest thing then would be to get this wheel and install this. I'm not sure if this wheel is available on pip, but if you guys are on Windows, then maybe get the Pi 2, Pi 3 x64 or AMD 64 wheel and install it on Windows, right? So you can install this wheel via pip itself. Like if you have working Python pip installation on Windows, then you can just use this. And if you want to get a pip installation setup, I think the easiest way to just install Conda, and Conda comes with pip, so that'll be sorted for you. But yeah, if you guys have any issues or if you can't install it, facing any sort of issues and you want to troubleshoot, do like reach out. Harsh and me and sir, like we'll all try and help you out as much as we can. Um, but yeah, I think for Linux you should just go ahead and get these releases. I think this x86 64.whl will probably work for most people. Um, sorry, AMD 64 WHL on Windows will probably work for most people. So yeah, this is the last one here, right? So you can install that via pip, and then I'd suggest you to just try out. I'll upload this file, right? Just try out running this, commenting out some of the assertions and running this. You can run it and then maybe comment out all of the diagonal assertions, and then also run it that after that, and that should give you a model. So you can use that as a sanity check essentially, right? Um, okay, so that's all I had. Are there any questions or anything? Okay. So people who are on Windows, this is uncharted territory for me as well. Uh, but yeah, let's try and figure this out together. Try to see if this works, um, and let me know what happens. Yeah, I will, but I don't think I have time today. But there will be another tutorial for that definitely. Yeah, there will be like tutorials dedicated to the Python API because there's a lot there. Um, yeah, it's actually much more interesting and flexible. So this was just to give you a flavor of doing things in Z3, and you can actually kind of get far and with just SMT2. There's also another thing which you can do is basically write SMT2 files from inside Python and then call Z3 as an external process on them. That sounds horrible, but that is actually sort of independent of what solver you use. So it'll be really easy to switch Z3 for some other solver if you do it that way, for example. And there are libraries which do that. Like they'll give you an API up front, but behind the scenes they're just writing to a file and then calling it. Okay. Are there any questions? Sure. So if there are no more questions or anything, then this is all I had. All right. Sure. Thanks for coming. See you guys later.